Hello everyone, we're here to introduce our fluid system, which is a simple house toilet. So the setting of the toilet could be any individual house or building. It is standard size with standard plumbing. There are no extra systems or additions such as a bidet or electronics. The purpose of a toilet is to remove waste using only water pressure and simple lever mechanics. So how does the toilet work? Once the water level in the tank goes below a certain height, it causes the float ball to lower, thus opening the fill valve. The fill valve, which is now open to atmospheric pressure, ejects out water due to the pressure difference in the pipe and the tank. Using the lever on the tank in order to flush, then raises a flapper at the bottom of the toilet tank, which releases the stored water into the bowl. With the excess water now reaching the steady state of the bowl's water, this causes the water in the trapway to reach over the hump, which then causes a siphon effect to happen, which brings it with it the water and waste in the bowl. So these are the portions of the toilet system that could be analyzed using fluid principles. The refill valve applies both work energy principles and the impulse momentum principle. The pipe that connects the toilet to the sewage system and the pathway from the tank to the bowl applies the continuity equation. The forces that are acting on the inside of the tank applies hydrostatic forces.
So the first principle that we're going to look at is applying hydrostatic equations. This is the force that the water is acting on the tank. The equation is force equals rho GHC times the area. We had to split it into two groups of equations because the left and the right walls are one dimension and the front and the back walls are another dimension. So that when you calculate the area, that impacts it. So for the left and right walls, the forces on each of them are 17.5 pound force. And the center of pressure on that is 7.33 inches. And then the force on the front and back walls is 45.7 pound force with a center of pressure of 10.3 inches.
And looking at the curved surface, which is the flapper at the bottom of the tank, it is a half dome, and we have to now include the weight because we're acting in the y direction. And the forces in the x direction will cancel out, but they do equal 1.55 pound forces. The forces in the y direction, the Fy is 3.09 pound force, and the weight on each side is 0.0523 pound force. So the resultant force would be the force in the y direction plus 2 times the weight, which gives us 3.19 pound force, and this will act completely straight down as there are no x components, positive or negative. And looking at the continuity equation, we are looking at the tank exit and the sewage exit where the water from the bowl leaves. We know the volume of the water, and we know how long it takes the water to flush, which is 7.3 seconds. So we can then find the volumetric flow rate. And using this with the continuity equation of the volumetric flow rate is equal to the area times the velocity of whatever section you're looking at, we can find the velocity out of the tank is 2.96 feet per second, and the velocity into the sewer from the bowl is 6.62 feet per second. And applying the work energy equation is tough to do initially because there is no work or energy added to the toilet. However, we added a pump and said that the pressure in the pipe feeding the tank or feeding the toilet was too low. So we assumed that the pressure feeding the tank was 11 psi, which is about half of what it should be in a regular home, and that the volumetric flow rate at that point was 3 gallons per 3 minutes as opposed to our ideal 7 gallons per 3 minutes. Using this and the work energy equation, we can then take out the HE and HL as there is no turbine or losses. The horizontal datum is where the pump is, and P2 is a free stream, so that does cancel. And in the end, we get a useful head of 34 feet, and then using the power equation for horsepower, we get 0.0205 horsepower is required, so not much. Now, applying the impulse momentum equation, we look at the trapper exit into the sewage, and then we see that our V1 is equal to the V that we got before, which is 6.62 feet per second. And our V2 is 59.7 feet per second using the continuity equation. Again, using the work energy equation, we can cancel out useful head, turbine head, and head loss. Z2 is the horizontal datum, so that does cancel, and P2 again is a free stream. So our pressure at 1 is 3,400 pound force per feet squared, and our momentum equation uses the volumetric flow rate and our change of velocities, and once those are set equal to each other with the forces in the y direction, which include the weight because we are acting up and down, we get a force on the wax wing, which is what we are currently trying to find the as our current unknown, as 340 pound forces. And
so with all of this information, some improvements that we can make is that we can add more toilets with 2 different levels of pressure in their flushing systems. This prevents water loss. So for example, if there's waste that is liquid, it requires less pressure than waste that is solid. Another type is vacuum assisted flushes, which allows them to be stronger. It reduces the chance that the toilet gets clogged and that there's less condensation on the tank. We can also add a nozzle within the trap that could jet out some water to remove any blockage that could be left over. The last thing we could do is decrease the size of the flapper, which would increase the velocity of the water. These are references that we used, and thank you for watching.